another day of market design. This is sort of auction day on market design, and the market design so far. The rest of the market design lectures emphasize matching, and there's a lot in auction market design. I won't be able to tell you about all of it today. And in fact, Al yesterday promised that I would tell you about some stuff that wasn't on my agenda. So Al, this is Roth's imperative. I have to tell you a little bit about product design issues before I get started. And this is very timely because I was actually on the phone with a major spectrum regulator last night talking about this exact issue, Al. This is precisely what we were talking about. So, even in matching, you could imagine what we call product design. That is, you could imagine that instead of hospitals having positions, one of the things they had was a pair of positions. It was a different product that they offered to a couple and hired both of them. This may or may not be a good idea for matching, but it's been a problem that's been around in auctions for a long time. So I will tell you a historical story just to build this up. I helped create the first U.S. spectrum auctions in 1993-94. And the first auctions were regarded by outsiders as wildly successful. I won't tell you what my own assessment was. But the rules basically were a version of a Kelso-Crawford-like algorithm. They were an ascending auction for multiple products at the same time. And there was quite an enthusiastic response from the worldwide regulatory community. And I met with some Australian regulators. And they said, this is great, but the licenses are too big. We should be selling postage stamps. That is, licenses that cover very little area and are really thin slices of spectrum. And then people can put them together however they want. Okay, that's what they said. And I started thinking, holy cow, that won't work well. Why not? Because they're not substitutes. Because there's minimum efficient scale involved then. And if you have licenses that are too small, you could end up in the course of an auction, winning, the coverage of the podium up here without covering the auditorium, right? You need these licenses in combination to make any use of them. So that period of time was the birth of combinatorial bidding in spectrum anyway. There had been some other combinatorial bidding. But in spectrum auction, the idea of combinatorial bidding came up where people would be able to put together their own packages. But meanwhile, we continued for a decade and a half to more than a decade and a half to continue mostly to use this version of a Kelso-Crawford algorithm. And now we were intensely aware that the licenses didn't have to be substitutes. And part of the question became, could you design them so that they are substitutes? Maybe that's part of what the regulator needs to design, is what products to offer. And that actually is an important thing that needs to be designed. So all I'm going to tell you about it in this case, the discussion I was having last night with the regulator, is should they be selling spectrum in individual 5 megahertz licenses, which need to be used in combination, because there's a fixed cost in setting up a cell network. If somebody is going to set up a cellular network and your phone is going to use it, they have to put in a radio that's going to use those frequencies, and they have to build those into their cell towers. That's essentially a fixed cost. And if they have more spectrum, they amortize that fixed cost they spread that cost over a wider range of spectrum that is being used. So should they be using individual 5 megahertz licenses so that the bidders can optimize who gets exactly how much? Or should they use 20 megahertz licenses, which makes the licenses more nearly substitutes and protects the bidders against this aggregation problem that they might buy too little and not be able to, so this makes the licenses more nearly substitutes. And so the discussion we were having last night is that there's an interaction between the auction design and the product design. If you design the products this way and make the licenses more nearly substitutes, you can run a Kelso-Crawford-like algorithm and have it work pretty well given that restriction. Or you can eliminate that restriction and use a more complicated combinatorial auction that lets bidders put together their own packages. But then you have those auctions. I won't tell you about them in general, but they're quite a bit more complicated than these. Okay, so Al, that was because you promised it. That's the extent to which I'm going to deliver on product design today. There are a lot more issues in product design. In the U.S., I'll say one more. In the U.S. at the FCC, one of the big issues that we've been talking about for the incentive auction is how big the geographic areas that are covered by a license should be. Should they be enormous so that AT&T and Verizon can be sure that if they buy a license they have national coverage? or should they be small so that a rural telephone company that wants to provide service to its own area can bid to buy that service? And so there's a tension between what the bidders want and how the product design enables creating an auction that where the bidders can meet their needs. Right? Anyway, real-world auction design. Yeah.
What are the objectives of, let's say, this kind of auction? Maximizing return to the seller, or is there also consideration of, public good? What is best for the population?
So again, I don't want to get sidetracked on this because this isn't my main theme for today. But the general answer is, first of all, that it differs by country. For example, in the UK, the spectrum regulator is by law not allowed to consider revenue when it designs an auction. In the US, the Democrats and the Republicans differ, and so there isn't a single, I work for the FCC. They have both Democratic and Republican commissioners. The Republicans are more concerned about revenue because of the deficit. The Democrats are more concerned about making sure that we build the infrastructure of the 21st century, as they call it, have lots of spectrum out there so that we can have broadband internet on which other businesses are built. So there isn't a simple answer to that, and an auction designer has to stay flexible. Okay, so what I want to talk to you about today is the most exciting thing going on in auction development right now, which is, this is based on a paper that I've written with Ilya Segal, and it's based on our work consulting. I had a consulting team for the FCC that's designing the new incentive auction in the US, and it's enormous. The Congressional Budget Office estimates $55 billion in transactions. They've estimated $40 billion on the buy side and $15 billion on the sell side. Those are just numbers in the wind, right? Nobody knows what the real number. If we knew what the numbers were going to be, we wouldn't need an auction. But but it gives you an idea of the magnitude of the thing. There's a lot of money at stake. And what's it about? So, and by the way, it's very current. Most of the rules, or the heart of the rules that we proposed, were adopted June 2nd, just adopted, so they are going to do this more or less the way we have proposed. And what's it about? It's a proposal to reclaim, now more than a proposal, to reclaim public airwaves now used for broadcast television and auction them off to wireless broadband networks with a portion of the proceeds paid to the broadcasters. That's the gist of it. So here was the problem. Right now, the spectrum uses have grown. There's many good uses of spectrum. We used to have spare spectrum that we'd allocate to new uses as they came along. All the spectrum with good propagation characteristics is allocated, and some of the old uses are no longer good uses. So broadcast television in the United States, as the founders of this, the people who are running this seminar well know, we used to watch television over the air with the rabbit ear antennas on our TV. Then we might have had fancier antennas on top of our homes. Nowadays in the United States, more than 90% of the population receives their signals either through satellite or cable television. Less than 10% is still getting their main television signal with over-the-air broadcast. The value of that spectrum in over-the-air broadcast is much lower than it used to be, and meanwhile we have a critical shortage of spectrum for mobile broadband. So we want to get that spectrum away from the broadcasters and into the hands of the mobile broadband networks, and the broadcasters don't want to give it away, even though they don't quote-unquote own it. So they just have licenses, but they've resisted fiercely any attempt to take it from them. And in 2012, in some very strange politics, as part of the payroll tax extension, the government needed some offsets to the payroll tax extension, so they approved an auction of radio spectrum because of the $25 billion in net revenue that it supposedly generates. And what the Congress decided is that the law will be that the broadcasters have a right not to the channel on which they're broadcasting. They can continue to broadcast at the same location. They can continue to cover the same population, but we can move their channel, or they can sell their broadcast rights, and we can clear the spectrum from them. So that's the law as of February 2012 in the United States. Okay, so the overall structure of this thing is going to be like this. I'm going to explain why it requires new design as we get into this. There's going to be a reverse auction, as we call it, to buy television broadcast rights. There's going to be a forward auction to sell mobile broadband rights, and there's going to be a clearing mechanism to jointly determine how many channels to clear and how much bandwidth to sell in the forward auction. Okay? Those are the three pieces. It sounds like supply, demand, and equilibrium, right? Okay, and by the way, when I do this, I like to make sure that people don't forget Evan Correll, who's the economist at the FCC, who had the really genius step, the single most important step, by far the most important step in this whole thing, is that is the definition of property rights. So again, market design, property rights are part of market design, and it wasn't clear what rights the broadcasters had, and Congress settled that along the lines that Evan had suggested, which is that a broadcaster has the right to broadcast, but not to the particular channel that it's on. And that creates competition. So if I'm trying to clear, let's say, channels 38 to 51 from television broadcast to use it for mobile broadband, and Eric owns a station on channel 44 and tries to hold out for a high price, I can buy Ken's station on channel 24 and move Eric down from channel 44 to channel 24 and clear the spectrum. So this definition of property rights creates substitution, and Evan Correll is the guy who figured this out. He's really the guy who deserves the applause for this whole big idea. Okay? That's a product design issue too. You're right. Although it's a property rights issue. So property rights affect the kinds of markets that can work. There's a lot involved. Now, this is my University of Chicago slide. When I talk, the computer scientists don't need this, and there's probably still a few economists out there, so I'll do this slide quickly. You might have asked yourself, why is any intermediary needed at all? Why don't we just let the broadcasters have the full right to use their spectrum, however they desire, and just trade it? Sell it to Verizon or AT&T, and why don't we do that? And the answer really is that this is actually a collective action problem. Because you'll see, I'm going to describe the problem in somewhat more detail in a moment. But what we need to do is, if we need to decide what bands we're going to clear, and then we need to clear all of those bands in every region of the country. If we decide we're clearing channel 38 to 51 on the basis of bids, we need to take everybody who's in channel 38 to 51, and we need to move them, either buy their rights or move them down into some other channel. This is a complicated, interlinked collective action problem, and we have to respect very complex, as you'll see, interference and other engineering requirements. So this is not something that can be done one little piece at a time, like hill climbing a convex function. And if we need an intermediary, why should it be the government? So why not just, this has been proposed actually by some right-wing economists, so why not just create an overlay license so that, Eitan over there has the license that allows him to do all the stuff I'm talking about, and he goes and negotiates with the broadcasters, instead of having the government do it. Why do we need the government involved? Why not just create these rights and let the market do it? And the answer is that a successful intermediary has to have and exercise power to specify lots of things. We're going to talk about, well, if I move you from channel 44 to channel 24, is there too much interference? Do you really have the same population, or is that that little area that you're not covering anymore, is that too substantial to let you do it? Somebody has to say what constitutes, reasonable interference, and somebody has to have the power to actually require the broadcasters to move. And so these are essentially governmental powers, which is why we need either a governmental or quasi-governmental agency to do this. I'm not sure that engineers needed that, but University of Chicago economists definitely need it. Okay. The repacking challenge. So here's I'm going to tell you about the repacking problem. So this is at the heart. This is going on during the auction now. Okay. So we have broadcast interference constraints. We have stations that are located in various parts of the country. Think of them as nodes in a graph. And I'm going to draw an arc that connects two stations if they would interfere if I were to assign them both to the same channel. So if I assign, both of you to channel 25, you're too close to each other, you would interfere. There's an arc that connects you. A set of bids in the auction is acceptable if the rejected bidders and the non-participating stations can be repacked into the reduced set of channels. So now I'm going to move everybody down into channels 14 to 36, let's say. if I can move everybody down, then it's feasible to select to accept that collection of bids because I can meet the constraints that I have to meet. But testing whether it's possible to assign a group of stations to a set of channels, that's a graph coloring problem. It's a problem that's well known in computer science. Graph coloring means assign a color, in this case a channel, to each node such that any two adjacent nodes are a different color, that is, are assigned to different channels. Okay, that's a graph coloring problem. It's NP hard to answer the question, does there exist a way to assign a set of stations or a set of channels to a set of stations so that so that there's no interference. NP hard means roughly that if P is not equal to NP for the computer science, it means roughly speaking that the amount of time that it takes in worst case to solve this problem grows exponentially with the problem size. And these problem sizes are large. There's about 130,000 constraints. And we're going to be checking about 1 million combinations of bids during the course of the auction. So we're going to be solving a million large-scale NP-hard problems during the auction. That makes this a really challenging market design. To give you an idea of what the constraints look like, the first thing that was done was that the government conducted an engineering study to figure out which stations interfere. And this, we pixelate the United States into these 2-kilometer squares. Actually, this is sort of a worldwide standard. You create pixels. You calculate, based on an engineering model, the signal strength at each area and determine whether the signal could be received. So some areas that are within reasonable radius can't be received. Maybe there are hills in the way that block the signal. And some areas would create interference. And you set a standard, such as, in this case, 0.5%. If these two broadcast towers within their service areas overlap with a population that's more than 0.5% of either of them, then they're considered interfering. And then we create this arc. So that's what's done. Here's what a point in the northeast looks like. This is a particular station in the northeast. And all of these pink stations are on the graph, on the interference graph with that station. Okay, so there's a lot of constraints, especially densely in the northeast of the United States. This is this is basically just there's no map of the United States on here. This is just the links from the interference graph, and it's and it's actually not all of the links. This thing is actually connected all the way. But this is almost all of the links. These are the so-called co-channel constraints that are graphed here. I simplified my description of the constraints. There's some other constraints too, but what I told you is enough for you to know that it's a hard problem. Okay, so this is just what the map looks like. The constraints are really dense over here and on the West Coast, and not too serious in most of the central United States. Okay, this is, if you like spring-loaded views, that's what the graph looks like. You know, it just doesn't have, here you can see better that there aren't really clicks that separate. There are the West Coast does connect eventually to the East Coast in the spring-loaded view of the graph. Okay, so how do we solve this problem? So the first thing I want to tell you about is the computational innovations. We had to have, this is market design here involved actually being able to do these computations. And the computer scientist on my team is Kevin Leighton Brown from the University of British Columbia. And he's sort of the main man in charge of seeing whether we can actually do this computing. And here's how Kevin formulated the problem. So we're going to have logical variables. XS comma C is the name of one logical variable. And it means that station S is assigned to channel C, true or false. There's one such variable for every station in every channel. Okay? Then station S must be on one of its allowable channels. So for every station S, we have a clause, a logical clause of the form that either station S is assigned to channel C1 or station S is assigned to channel C2, and so on. Okay? Then we have a station can broadcast on at most one channel. So for each pair of channels, it's not the case that station S broadcasts on channel C1 or it's not the case that station S broadcasts on channel C2. These clauses have to be or clauses, so it's stated in that way. Okay, and then we have to have no harmful interference for pairs. So if this pair is infeasible, if it's not feasible to put station S1 on channel C1 and station S2 on channel C2, then you have not this clause and not that clause, or not that clause. Either we don't have station S1 on channel C1, or we don't have station S2 on channel C2. Otherwise, we would have interference.
What do you mean by an allowable channel?
Aha. Okay. So it turns out that, for example, we have a Canadian border, we have a Mexican border, we have a treaty with Canada that says certain channels are reserved for the Canadians and we're not allowed to use them. Certain channels are reserved for the Mexicans. Also, during the course of the auction, when we're deciding which channels to clear, we might decide we're clearing channels 38 to 51, in which case channels 14 to 36 are allowable. Or it might be we're clearing channels, let's say 31 to 51, in which case channels 14 to 30 are allowable. So
it's endogenous. Some of it is endogenous.
It will be endogenous. I'm going to talk about how you, given the set of allowable channels, how you check. And like I said, there's 130,000 arcs here, so there's even more of these constraints. There's one for every. Well, there's a lot of constraints in this problem. So this is a really large-scale problem. And so how do you go about solving this problem? So the first thing I'm going to talk about is the computer science contribution. What Kevin does is we do not have, so you'll notice, if I may go back a few slides. Oops, here. When we solve this problem, we're going to be clearing some of these nodes. And what we will have is a subgraph of the original graph. So we don't actually have to solve all graph coloring problems in the world. We only have to solve graph coloring problems on subgraphs of the existing graph, which in some sense is a very tiny dimensional subset of the it's a huge set, but it's a very small subset of the set of all possible graphs. So that's what we need to do. And the idea is to use machine learning to see if we can find, even though there doesn't exist an algorithm that's fast on all problems, the idea is to use machine learning to see if we can find an algorithm that's fast on these problems. So we pick a highly configurable SAT solver. The SAT solvers are algorithms for solving the logical problems I've described to you. And the high performance problem solvers like SAT problems are typically parameterized. So you have parameters that help you figure out how to branch when you're deciding which variable to check next for the branching heuristic, what order to check the variables in, what pre-processing to do. There's clause learning that goes on in these things where what happens is that as you start checking, it takes you a relatively large number of iterations to figure out something is impossible, but then you decide you could have figured that out quickly if you had only had this other proposition that logically follows from those. So you add that to your list of clauses so that it gets checked immediately, and so you can trim many branches of the tree all at once during the course of the algorithm. So clause learning goes on during the course of these SAT solvers. The clause learning strategy that uses another variable. There are our SAT solver has about 150 parameters, so what we do is we have a bank of computers that's running 24/7, searching this 150-dimensional space that is starting with configurations of the SAT solver, calling different parameter settings, using a data set that we have generated by running simulated auctions to figure out what SAT problems we have to solve, solving them, returning the cost, that is the time that it takes to solve the problem, and searching the parameter space. And there's a sophisticated algorithm for doing the search. It uses Gaussian approximation, as they call it, where it's a Bayesian-like algorithm where what you do is you have some data points where you know how they perform because you've run your instances, and you form a model based on that, and then uncertainty around the model, and then you look at which point, if you add next, has the greatest expected reduction in your minimum running time among all the points you know about, and you test that one next. And then you get another point, and you fit a new model, and you express uncertainty around all of that and figure out which point in that space maximizes the expected reduction in runtime, and you check that one next. And that's the algorithm that has been totally automated and is running in the background. And I'm telling you about this because the performance of this thing has been spectacular. Here's the performance. It's just amazing. So this is a cumulative distribution. I have a log scale on the horizontal axis and probabilities running from 0 to 1 on the vertical axis. These are cumulative probability distributions. And what you see here, these first points over here, are standard SAT solvers with their out-of-the-box configurations running on the problem. So the fastest ones, we're taking, 5 seconds or so on the slowest problems, and we were timing it out at 5 minutes. So this one, we're solving a quarter of the problem in 5 minutes or less. The fastest one out of the box was solving about 42% of the problems in 5 minutes or less. We took this poorest one and configured it, and it was doing much better. In 5 minutes or less, it was now solving 75% of the problems. And then we took the most configurable SAT solver and ran this thing on it. And the median runtime is now 1/7 of a second. And in 5 minutes, we now solve 98% of the SAT problems. Okay, this is if you take a look here, it's roughly 3 orders of magnitude improvement. It's really quite spectacular. I didn't know anything about machine learning when I began this project, and I have to applaud Kevin for a really amazing performance. Now, this 2% that's not solved here, if that stays the same, that's going to cost us $500 million in the auction. And because we're solving 1 million problems, and 2% of them is 20,000 problems that we will not be solving and correctly. So we have strategies for this. I wonder if I've got a slide about that. Yeah, so basically, one of the main ideas for doing this is there's several ideas. One of them is to use portfolios of solvers. So what you do is you take the 10% or so on which this algorithm was performing poorly and use that as a training set for a new algorithm, and find an algorithm that runs fast on the very problems this one was slow on. And then during the auction, you run them in parallel, and you take whichever one gives you the answer first. And if you can solve 90% of the problems that are hard for this algorithm, then this 2% becomes 0.2%. I'm sorry, 0.02%. Well, 0.2% if it's 90. And that saves a whole lot of money for the government. So we have ideas about how to get this number up close to 100% by running parallel processors and training algorithms and other techniques. Okay, yeah.
So these problems on which you tested the solvers, where do they come from?
So that's a great question, because I'm really worried about that. The question is, where do the problems come from? And that's important because we're training on a particular set of problems. When we run the auction, we're going to have a different set of problems. So the answer is that they're coming from simulations that we run of the auction. And what I hope to do if the FCC lets me, between now and the auction, I need budget for this because it takes people and machine time and so on. I want to start generating data that varies tremendously from the base case and have algorithms that are trained on a much bigger set of things that might emerge from the auction with different kinds of bidding. And if we are able to, and then test out of sample to see exactly, after we've trained on one sample, how well do we do on other samples until we've got this to where it runs very fast on everything. But that's part of the testing strategy. I'm going to get stuck on just questions, but okay, yeah.
Just a quick one. I mean, on those types of problems, you know that the assignments are unique or whatever? Or?
Oh, they don't need to be unique. It's yes or no. This is a yes, no. So what we need to do is know that we're getting the right yes/no answer. So the problem is, given a collection of bids, I'll tell you just a bit more about this. Given a collection of bids, can I accept them? The answer is yes or no. Okay. Then after the auction is done, when I know what collection of bids I've actually accepted, then we're going to run an optimization routine and try to do it in the best possible way. But during the auction, we're just getting yes or no answers. And when you run a SAT solver, if it tells you yes, You can check that it's correct because it delivers the solution. If you know what it means to be an NP-hard problem, is it delivers the solution. And you know, once you have the solution, you can check that it is a solution very fast. And if the answer is no, you basically can't check it. The only way that what we're doing to check the no's is having training other solvers. We're actually sending to other solvers that have days to work on them, the classes of no's, to see whether we're ever getting the wrong answer. So far, we're not getting any wrong answers. So we're pretty confident. And if you have a wrong answer with no, it just means you pay more in the auction. So if we have a tiny fraction of no's that are incorrect, it won't matter, and the yeses can all be checked.
And a computer science question.
Yep.
Another community that is interested in solving SAT problems are the people who are doing program verification, and they have practical satisfiability solving algorithms. For example, Ed Clark at Carnegie Mellon. Is there any interaction? Maybe.
So Kevin
maybe some of the
I need to cut you off because I'm really pressed for time here, and I don't want to take it too far afield. Kevin is an active member of the SAT solving community, participates in the SAT solving competitions, which work in lots of different areas. But in all of them, the winning algorithms are always tuned to the class of problems. So they have problems for, you know, testing circuit design. They have SAT solvers for, and the winning algorithms in the competitions are always ones that are tailored to the problems. You know. Okay. So I am pressed for time because this is there's a lot of material in here. So let me try to cut off asides and push forward. I want you to assume that each bidder owns a single station and knows its value for the stations. Now, this isn't true. Neither of these statements is true. The bidders don't all own single stations. However, the design is based on the expectation that the bidders who are actually going to sell are the small individual broadcasters who do own individual stations. If you have high-value if you're a Fox affiliate and you have really high-value programming, or you're a CVS affiliate, those guys are going to have higher values in the auction and are going to be less likely to sell. The bidders that we're most concerned about designing the auction for are the bidders who own single stations in an area, or maybe a couple of stations in different areas. And if they're in different areas, there's no strategic possibilities available to them anyway. If you own a station in New York and a station in LA, you can't withhold your station in New York and hope to get a higher price in LA. It's just not feasible to do that. So it's reasonable to use this as for the basis of a theory of how the market design works. It would be as if there were very few couples in the match or something. And the central thing that I've been pushing since the beginning on this is we have I know how complicated it is to bid in auctions. I give auction advice to bidders. And this auction could easily become extremely complicated for a bidder. You try to figure out, I put in a bid, what's going to happen, how much should I pay? It could be really complicated in a setting like this. And we don't want it to be complicated. We want it to be obviously strategy proof, what Al calls safe. We would like a bidder, you know, I'd like to be able to go to Eric and say, you know, Eric is feeling confused. He's looking at this. It's an amazingly complicated mess. And he knows that Al back there is a venture capitalist who's been buying up stations and has fancy consultants. And he's really worried that if he participates in the auction, you know, Al's going to get a high price for his stations and Eric's going to get a low price for his stations, and he'd rather just not participate and make a deal after the auction. If we have people who decide not to participate, that's deadly for this auction. We need bidders. If we're going to clear spectrum, we've got to have broadcasters who are willing to sell their rights. So that's why I want this auction to be strategy proof for small bidders, and not just strategy proof. I want it to be obviously strategy proof, a technical term if you ever heard one. I want it to be that if you have a station that's considering selling its broadcast rights, it doesn't have to say, gee, they're doing a VIC recalculation, they're solving two combinatorial optimization problems and taking the difference and quoting me, you know, and saying that's the price they're supposed to pay me. I don't trust the government to do that calculation. Maybe they made a mistake. They tell me it's strategy proof. How do I know that that's strategy proof? Maybe if I bid something else, it would be better. I mean, that just doesn't fly. I want it not only to be strategy proof, but to be obviously strategy proof. And I'll show you what we're going to do that. Okay? And preferably, I'd also like it to be group strategy proof. I don't want a bunch of station owners and an individual, you know, in New York or something to meet over dinner and say, look, why don't we all just hold out for a higher price? I want it also to be group strategy proof. So can you do that? And in order to maximize clearing and to increase the net revenue, I want to make the cost of acquiring stations not too high. I want to keep it low. It's got to be high enough. I mean, it's an auction. It's got to be high enough for the bidders to want to participate. But I don't want to drastically overpay any of the bidders in this auction. So that's the kind of design criteria that we had when we were going forth on this auction. So this is a challenging market design problem.
Is there any issue about sellers figuring out what their values are?
Yes.
If it were costly for me to do that.
Yeah, and knows its value for the stations.
Yeah.
So this is something I can't do anything about. So, sorry, I said neither of these was true. Neither of these is true.
Yeah.
The seller who's trying to figure out the value of its station has to say, well, gee, you know, my station isn't that good, but after the auction I might be able to sell it because there's going to be a shortage of broadcast channels after the auction. Maybe my station will be worth more than it is now, or than it was last year before people knew about the auction. I have to figure that out and decide what price. You know, that's a problem I can't solve. So I'm gonna brush for the theory. I'm gonna sweep that under the rug. But I will tell you that there are some things we're going to do about it, but they won't be complete solutions. Okay, we'll tell you what we're going to do about it as we go forward. One of the things that will help is that the broadcast industry is going to this is going to be a big deal in the broadcast industry. Just wait till next month, when the FCC announces the reserve prices for this auction. It's going to be headlines in the broadcast industry because there's a lot of money at stake, and they're going to be talking about it. And they're going to be talking about among each other, and there'll be consultants out there that will help. But there's more that we can do. Okay, so we're trying to encourage participation and keep the costs low. And I'm not going to talk about this. We actually we have to do more than this. This is the main option that bidders are interested in. But we also have a few, they could take cash for agreeing to go off the air, but we also have a few blank spots in the VHF spectrum. VHF spectrum isn't as good as UHF spectrum, but if you're like a university television station and you're currently broadcasting on UHF, and somebody says, you know, if you'll switch to VHF, I'll give you $10 million, a university might find that to be an attractive proposition, right? So the auction will also have to take into account the possibility that bidders will accept a smaller amount of cash to move to and accept either low VHF license or high VHF license in exchange. But and it'll also have to allow VHF station owners a chance to sell their stations so that we can move them out and make room for the UHF guys who want to move down. I mean, all of those pieces are going to be in. I'm not going to tell you about any of these pieces. They're also part of our design. So this is what Al would call a theory paper, because I'm not going to tell you about the actual problem, just the theory underlying the main problem. Okay, and of course, don't add excessive complexity. All right, so of course. Okay, so why don't we just run a victory auction? When we first came aboard, there was a serious proposal to just do a victory auction, have people put in their values, do all the calculations, and figure out the victory prices. There's more than 2,000 stations, so the average price of a station is less than about a 20th% of the value. And we're talking about low-value stations mostly. The victory price is the difference between the value of the total allocation with or without one station. So it's the difference of two numbers that's on the order of 100% of the total value. Now, the computer scientists were very pleased at how the operations researchers at the FCC at how well they solved this optimization problem. They ran Garobi or Cplex for 2 weeks and provably came within 3% of the optimum, which they thought was really good performance. Okay, now imagine that you've come within 3% of the optimum. You're taking the difference of two numbers. They're correlated, so I don't want to exaggerate, but you're taking the two numbers that can have errors as large as 3%, and you're trying to estimate a number that's on the order of a 20th%. Well, what we were getting out of those calculations is negative prices and outrageously big prices, and it was just nonsense. You can't calculate. Victory prices cannot be reliably calculated in a problem of this size. Okay? They're just computational problems. So second, the victory prices are hard to verify and explain. Again, I come up to the broadcaster and say, you know, you're supposed to bid truthfully, Inbal, you're supposed to bid truthfully, and trust me, I'm giving you a price that's calculated in a way that makes it in your interest to bid truthfully. And, you know, I'm the government, right? Do you trust me? You don't, is the answer. So, so this just isn't a possibility. Okay, and third, victory auctions are not group strategy proof. If the other two problems were solved, we might have settled for this, but we can get group strategy proofness. So, literature review, do I have time? I'll just do a rapid literature review. The seminal papers in the computer science literature that has to do with combinatorial auctions using heuristics instead of optimization. Lehman, O'Callaghan, and Schoen. And I won't talk about that a lot. There's some other heuristic mechanisms that are in the economics and computer science literatures, and some of them are related to ours. Again, I'm not going to talk much about the related literature because I'm pressed for time. There's also related economics papers that, you know, these are deferred acceptance auctions. It's related to the entire matching literature, among other things, along with various other parts of the auction theory literature. Okay, so I have to tell you what I mean by deferred acceptance algorithms in this case. And again, as you see, I've been, you saw yesterday, I tried to take a unifying perspective. I tried, what is really going on? What's the central thing that's going on? And as I told you yesterday, I think deferred acceptance had an unfortunate name, which we've decided to live with. What's really going on is greedy rejection. That is what really goes on in a deferred acceptance algorithm. Every algorithm sort of makes its choices at the end in some sense, but what are the commitments it makes along the way? The commitments it makes along the way are to reject some bids, some offers, and then never to revisit them. That's how the algorithm makes progress. So deferred acceptance is greedy rejection, okay? And that's going to be the idea that's going to come up in this auction too, okay? So in my model, each bidder has a finite set of possible bids, which are positive real numbers. Each bidder's possible values lie in some compact interval, so you know your value can be pi, but your bid has to be 3. Okay, that's the way the model looks. Given a profile of bids B, the set of winning bids is denoted by alpha of B. We're doing a revelation mechanism. I want you to imagine initially this is a sealed bid auction. You say, you know, the lowest price, my bid for my station is, you know, $20 million, and Eric says the bid for my station is $150 million, and Ken says $1 million, and I pick the set of stations that I want to buy. Okay? Bidder J's threshold price is defined to be the highest bid that, given the other bids, would be winning in this procurement auction. Remember, lower bids tend to be better, so you take the highest bid that would be winning. And we're going to say that an auction is strategy proof if for almost all values, reporting the true value rounded up to the next higher bid is a weakly dominant strategy. So, you know, you don't get to report your actual value if your value is pi, but you could report 3 or you could report 4. And when your value is pi, I want you to report 4. It's that's what I'm going to mean by a strategy proof auction. And the reason it says for almost all values, Eric is looking, is because if your value were exactly 3, in this auction you're going to be indifferent between bidding 3 or 4. So so won't be dominant as dominant is usually defined. That is, there won't be any profile of bids for which 4 is actually strictly better than 3. They'll always lead you to exactly the same payoff for some non-generic values.
Why do you limit the set of bids to a finite set?
Well, it is limited to a finite set, and in reality, and it makes the theory real easier too. You'll see. I'm going to describe the theory. This theory is, you know, like matching theory, is discrete, and when preferences are strict, like matching theory, it makes things easy. And preferences are strict almost all the time. So you know, think of this as being in the family of matching theory models instead of in the traditional family of auction models, and discreteness comes naturally. Okay, well-known theorem. This theorem has appeared so many times I don't know who to credit it to, but the auction alpha, which determines the winning bids out of a set of bids, and P, which determines the prices that bidders pay, is strategy proof if and only if alpha is monotonic. That means that if when you bid 100, that wins. If you bid less than 100, you still win. Okay, lower bids are more likely to win. And second of all, P is the corresponding threshold pricing function. Okay, it's not hard to prove. It's, the same logic as a second price auction. A threshold is set for you by the bids of the other bidders, and if you bid less than that, you're a winner and you get that price, and if you bid more than that, you're a loser. Then it's going to be in your interest to report truthfully, essentially, and truthfully means rounded up to the next whole number because that's how the threshold prices are defined. Okay, so here's what a deferred acceptance algorithm is. Okay, so we're going to start with a finite set of bidders n, who have a typical bidder I. And we're going to take a look at a product set of bid profiles. This is a finite set that specifies a bid for each bidder. And it's a finite set of positive real numbers. And each bidder is going to have some set of possible values on some interval. And during the algorithm, there's going to be some set of bidders who are still active. So A is going to denote the set of still active bidders. And there's going to be a scoring function by which I determine how good your bid is. And during the algorithm, I'm going to proceed, basically during the algorithm, I'm going to proceed by rejecting a bunch of bids. And so what I'm going to do is Ken has made a bid, and I'm going to look at his bid. I'm going to look at the set of active bidders. I'm going to look at the bids that I've already rejected, the bidders who are not still active, and I'm going to come up with some score for Ken. And any constraints, I'll explain how in a moment, will be encoded into this score. So what will happen is I'm trying to reject high bids, so this will be an increasing function of B. And if it's infeasible to reject Ken's bid because there's no channel that I can assign to him, that constraint will be encoded in here by giving him a score of 0. And I'll know that from the set of still active bidders. Okay, so the constraints are encoded into the score. And then different deferred acceptance algorithms are distinguished by their scoring functions. And here's what this is it. This is the whole deferred acceptance algorithm. Very simple. We initialize at round 1. The set of active bidders is everybody who's volunteered to participate in the auction. If everybody has a score that's 0 or less, we stop, and we accept all the active bidders, say your bids are winning. If not, then we find the guy who has the highest score, in other words, the guy who has the worst bid according to our evaluation criterion, and we reject him, and we set the new set of active bidders equal to the old set of active bidders minus the guy who we've rejected. So think like the man offering deferred acceptance algorithm. What happens is that at least in the formulation I gave you yesterday, is you think that everything's available to you, and you reject you get an offer, you reject that offer because you have better offers. That offer is now gone out of the active set. Okay, and then you increment and iterate. That's it. Not very complicated. Okay. So I call this a deferred acceptance algorithm. It's iterated rejections, just like the man offering deferred acceptance algorithm is in matching theory. Okay, why do we have a scoring function? What does scoring do? Well, as a first example, the score might be the bidder's bid itself. It becomes 0 when the bidder becomes infeasible. And then it's just sort of a greedy rejection algorithm. I take the highest bid. If I can reject it, I reject it, and I give it a channel. And then I go down to the next highest bid, and if it's possible to reject it, I reject it, and give it a channel, and so on. And if it's not possible to reject the next highest bid, I change his score to 0, and I move down and take the next highest bid and see whether I can reject him. If it's not possible, I change his score to 0, otherwise I reject him. And I continue that way through the full set of bids until all the remaining scores are 0. Okay? Another possibility that turns out to work pretty well empirically in our data is that you can take a bidder and divide it by its degree in the interference graph, or its degree raised to some power. That has the effect that that I try not to pack stations that, if I were to put them on the air, would interfere with a lot of other stations. So let's say Danny over here has a station that would, he has a really high bid, and I'd really love to reject it, but if I put him into the interference graph, that is, if I assigned him a station, he would interfere with lots of other potential stations. Then I'm disinclined to do it. I reduce his score by doing this, okay, and makes me less likely to reject him. Now, Inbal, you guys have studied these algorithms doing worst case analyses. We've sort of have optimized the scores for the particular graphs that we're looking at, and this actually performs very well on our data. Third, a bidder score could depend on the set of remaining items. So it could be that I have a limited budget that I want available to spend, and I can figure out what the threshold prices would be, and the set of bids that remain, how much I'd have to pay. And if I can't afford to buy all of this, in our auction, for example, the amount of money that we can spend in the reverse auction is going to depend on the income we get from the forward auction. So if we're not generating enough income from the forward auction, we can just continue rejecting stations. Say we're just not going to be able to clear as much spectrum, and the scoring rule can adapt to that endogenously by making the score depend on the set of remaining items. It can depend on it can allow benchmark pricing, which we're also planning to recommend for the to the FCC. Benchmark pricing means that what we're going to do is so we don't know what reserve price to offer, and I've told the FCC, and I think the FCC, well, my recommendation to the FCC has been that they set the reserve prices really high. I won't tell you what high means, but it's a big number, because I want the competition to drive the prices. But the problem is there are some areas where there's not much competition. So along the Canadian border, we don't have very many channels available, and we might need everybody who offers their station. And then if we set the reserve price really high, we could end up paying really high prices for stations near the Canadian border. So what do you do about that? Well, what you can do is you can make the score of a bidder depend on the previously rejected bids. We can take areas where there is competition. For example, we can take a look at in New York City and see how much per population we're paying for broadcast stations in New York City, and we can say, we're going to reject any bid that's in, in some sparse area along the border that has a price per unit of population that's higher than the price we're paying in New York. So we can score based on the bids that we've already rejected from other metropolitan areas. That's called benchmark pricing, and that's also possible to implement through the scoring function. The scoring function is really flexible. And finally, if we wanted to, allow impairments in some places, we could proxy for the cost of accepting impairments by using the population of the station. We're allowed to, the index of the station is also one of the arguments of the scoring function. So we could say, you know what, it's true we can't do without your station, but you're only interfering with 50,000 people in some remote area, so we don't care. We're just going to we're not going to pay you more than this, and if you don't want to take it, we'll just accept the interference. Okay, so I'm going to give you an informal summary of the main theoretical results of the paper. Then I'm going to cover as many of them as I can. And the other thing I want to do for you before I finish today is so I've moved it up ahead of some of the theoretical results, is to explain the clearing. Because so far I've focused just on the reverse auction. I don't really have much time to talk about the forward auction, where all the product design issues come up. But I want to show you how we paste the forward and reverse auction together, and you're going to see Marshallian dynamics come up there. I mean, these ideas are coming from everywhere that we pull into market design. So here are the main results. First of all, every deferred acceptance threshold auction is strategically equivalent to some descending clock auction limited to cutoff strategies, which I'll define in a moment, and vice versa. Cutoff strategy says, Ken says, you know what, my station is worth $50 million. I will not take less than $50 million. So in a deferred acceptance auction, he bids $50 million. In a descending clock auction, what happens is that there are clocks that are in front of each bidder that are descending. And Ken's clock starts at $100 million, and depending on bids others are making, it ticks down to 90 million, 80 million, and a cutoff strategy for Ken says that he's going to stay in until it reaches some cutoff. He's named $50 million. And the point is that algorithm essentially is a deferred acceptance algorithm. In fact, there's a one-to-one mapping between those algorithms and deferred acceptance algorithms. So these clock auctions are therefore strategically equivalent to deferred acceptance algorithms. Okay? The second theoretical result is that every descending clock auction, even if you don't use the cutoff strategy restriction, is not only strategy proof, but it's group strategy proof, which is to say there does not exist any set of bidders who, by changing their bids, could all benefit strictly. Third is that the price and allocation from, so these are, you can see why we want these things. The group strategy proof. I've explained to you, I want to be able to say to the bidder, Mr. Bidder, this is safe for you to participate. You're going to get the same price for your station as that hedge fund is getting for his station, to the extent that your stations are close substitutes, right? If they're identical, you're going to get the identical price. There's no strategy in this auction. You should participate. But in addition to that, when I first proposed this, I walked into the office of the then chairman of the FCC, Julius Janikowski, and his concern, which I knew was going to be, was, how much is it going to cost us? I mean, wouldn't it cost us less if we just had these guys bid and pay their bids? Some of them would pay their bids. And I told them the first story I told them, look, if you do that, they might not participate. You have these small bidders who are afraid of, I know this from advising small bidders. So one of the guys used to talk about the schmuck factor, which meant that he didn't want to feel like a schmuck after the auction, like he'd really done badly. And he didn't like to participate in an auction if he was going to feel like a schmuck when he was done. Okay, so I know that bidders care about this stuff. But besides that, the question, what about the price on average? Is the price a lot higher if we have to do this? Is it, well, how do you tell them? The paid as bid auction, we can't calculate the Bayes-Nash equilibrium of the paid as bid auction that looks like this. So how do you answer that question? So I gave them the best answer that we know, which is this. The price and allocation from the deferred acceptance threshold auction is the same price and allocation as the unique full information undominated Nash equilibrium outcome of the corresponding paid as bid auction. So what we can do is we can do a full information Nash equilibrium of the paid as bid auction. In case anybody has ever wondered, would a consultant dare go talk about a full information Nash equilibrium in front of a real person when we all know that, how iffy that is? The answer is yes. Okay. And it's because there's nothing else to do, right? You need a standard, and there isn't another standard that we had. This was the best standard we had, and so we used what we've got. I'm sorry to be the guy standing under the light pole, but that really is the best standard that we had available. And because this is contrary to the theorems in combinatorial auction theory. In combinatorial auctions, we know that the revenue from a Vickrey auction is less than the revenue at a full information Nash equilibrium, the Bernheim-Winston full information Nash equilibrium paid as bid auctions. They're not the same, and providing incentives is costly to you in a general combinatorial auction. So it's interesting that it's not costly to you at the paid as bid, and moreover that there's a unique outcome. There's not a unique Nash equilibrium, but there's a unique Nash equilibrium outcome of these auctions. The losing bidders can vary their bids in arbitrary ways, but the winning bidders always bid the same at every Nash equilibrium. That's also pretty surprising. Okay, and then the last of this, so okay, this one is for you, Eric, and for you, Ken, right? So here's an insight for you guys. So suppose that you try to analyze a paid as bid auction game by eliminating dominated strategies. So I take the auction, I eliminate the dominant strategies, I have a smaller game, I eliminate the dominant strategies again, iterated elimination. That's a deferred acceptance algorithm, okay? Because the set of strategies that you have left is what you've got left. What you do is you reject, find a smaller set, reject, find a smaller set. Okay, so iterated elimination of dominated strategies is a deferred acceptance algorithm, and that idea is at the basis of this result. Okay, if you take I'll tell you what non-bossy means for those of you who haven't studied this yet. If you have a non-bossy paid as bid auction that's dominant solvable for generic values, it's a deferred acceptance auction. Okay, the only dominant and the reason we get uniqueness up here essentially is because these games are dominant solvable. Okay, that's where this comes from. Iterated elimination of dominated strategies is a deferred acceptance process. It involves rejecting some things, taking the remaining set, rejecting some things, and so on. Okay, so those are the big theoretical results, and I'll show you. For those of you who don't know what non-bossy means, here it is. Suppose I have some rule that takes a set of bids and decides which of these guys to assign. This rule is bossy if for some bid profiles B and C and some bidder J, if J changes his bid from B to C, it does not affect J's allocation. It doesn't affect whether J is a winner or not, but it does affect somebody else's allocation. Such a mechanism is called bossy, and bossiness has mostly been used in matching theory so far. It's called non-bossy otherwise. We want to use bossy mechanisms, in fact, because when we do thresholds, when we compare the price, when we base the price that we're offering to the station in the remote area on the bids in New York City, that's a bossy mechanism. The losing bidder in New York City can change his bid in a way that doesn't affect his allocation, and it can change whether the guy in North Dakota or wherever is also has a winning bid. So we will use bossy mechanisms. So budget-constrained scoring rules, yardstick competition are bossy. Surplus maximization, and the first of the deferred acceptance rules I showed you are non-bossy. And every non-bossy mechanism leads to, well, this theorem applies to. Yeah?
So it's only bossiness in the allocation, not in the price.
Right. These are paid-as-bid auctions. Well, I'm looking at the allocation.
Not the price.
And whether it's bossy in the price depends on the auction rules. I'm looking at paid-as-bid auctions, so they're never bossy in the price. Okay, they can only be bossy in the allocation. Okay. You know what I should do? I'll do this and then, okay. So what I will do is tell you, first of all, about the equivalence to clock auctions, because this is really important for the implementation. So in a clock auction works like this. Remember, it's going to be mappable right onto a deferred acceptance auction. So I'm going to write the clock auction this way, that at any round of the clock auction, the way the clock auction works is that all of you guys are bidders, and each of you has a screen in front of you that's got a digital clock on it. And they're discrete. It ticks down one increment at a time, okay? And sometimes it doesn't tick at all. Sometimes it just seems to freeze for a while. Okay, so that's what you're looking at. And you have yes or no in which you say, yeah, I would take that price, or no, I wouldn't take that price. If you say no, for you the auction's over, you're out. If you say yes, you live another day. So Eric, your screen currently shows $100 million. Your station is worth $20 million. Would you take it? This is what I mean by obviously strategy proof. If you say no, you're out of the auction. If you say yes, you might get $100 million or some other price. So you say yes. It's just obvious that that's the right thing to do. And it turns out that I have lots of offers in your area. I don't need your station. I say, Eric, I have more offers than I need. I'm lowering the offers. Would you take $90 million? And you say yes. And said, I still have more offers than I need. Would you take $80 million? So that's how a clock auction, descending clock auction works. All right. So here we have the active bidders at round T is AT. The history is a super T of bidders who have been active at all the rounds before. There's a set of possible histories H that may prevail at any time. And we have a pricing function P from H into Rn plus. What the pricing function does says, well, depending on what's happened in the auction so far, I may change some of the prices. I show new prices on the clock, but the prices can only go down. The prices that I show to bidders at round T can't be higher than the prices I showed them at round T minus 1. Okay? So that's what a clock auction is. And I'm going to use ET to denote the set of active bidders who exit at round T. So when I get down to $20 million, because it turns out I got plenty of competition in Eric's area, he says no. So he exits and he becomes part of the set of exiting bidders. Okay? And for the theory, I won't tell you about the details of the implementation here, or maybe I will if there's more time. But for the theory, I want you to suppose that we're ticking one bidder at a time. In effect, the algorithm, the computer is ticking one bidder at a time. The bidders are looking at, would you accept a lower price? But I don't actually offer you that lower price until it's your turn, algorithmically. So here's how the clock algorithm goes. We set prices PAT for round T. If we haven't changed any of the prices, the auction's over, and the guys who are still active are assigned at those prices. Otherwise, we take the guys who have exited, right? And we increment T and we iterate. Yeah.
On the group strategy groupness.
I'm going to come. Okay, but go ahead.
Well,
yeah.
Suppose I exits
Mm-hmm.
early.
Yep.
It's not individually strategy proof, but that stops the clock from coming down.
Yep.
So Ken is able to get
Yeah. So
a nice high price.
So you notice that I was very careful in my statement. I used the usual definition of weekly group strategy proof, which means that you can't all strictly benefit. You didn't
So no transfers allowed.
No transfers allowed. Now I should say this comes up a lot, and so in real world market design, there's a big difference between collusion with transfers and collusions without transfers, because if you write a check, or Ken writes a check to you, there's a paper trail, right? When it makes a transfer, somebody observes it. All of a sudden, you're walking around with a lot extra money in your pocket. Somebody wonders where that came from.
Other ways of making transfers.
Any transfer.
Multiple auctions, for example.
Well, right. Oh, yes. Okay. Multiple auctions are another way. That's true. Okay. So but this auction there isn't multiple auctions. The law allows one. So and when a broadcaster goes off the air, the chance that he can collude with another broadcaster in the next auction is trivial. So this application, the weekly group strategy proof, is a decent concept. And again, I want to emphasize for everybody else that what I was starting to say is that if you can sit down with the other broadcasters, you're a New York broadcaster, and can sit down with the other ones and say, here's how we should all bid, and we'll all be better off, that's a lot easier to do without being noticed than if you say, go out at a really high price, so I get a high price and I'll write you a check. That's it's a much harder kind of collusion to do in practice. Scott.
What if you're a conglomerate of
Right. So again, remember I started by assuming that each channel was individually owned. It's not true that each channel is individually owned. It is true that most of the low-value channels are individually owned, or nearly so. And so the auction design focuses on them, and the theory is about them. Bidders know whatever they know. It doesn't really matter what bidders know for this theory. Okay, and there's an equivalence map that basically, I think I've made it clear enough just from looking at it that the exiting, if you make this an automated, if bidders use cutoff strategies, if Eric puts in a number like $20 million and goes out, that's exiting is like rejecting. And he's got $20 million. I reject a bid of $20 million, or he exits at $20 million. And you can go through and do, as we do in the paper, an exact one-to-one map between clock auctions and deferred acceptance auctions. And for any deferred acceptance auction, so here's what you do. At round T of the procedure, you determine which bidder J would be rejected next if all the bidders were to make their maximum still available bids. You call that price PJT, and you construct the clock auction by offering essentially a price that is below PJT, and he exits. If the bidder offers PJT, you reject it, and if you were to offer this bid in a clock auction below PJT, he would reject you, and so you get the same allocation from either the clock algorithm or deferred acceptance algorithm. And so this, if you implement the deferred acceptance algorithm this way, you can just create a clock auction in which you do exactly the same thing. Okay, I realize that was a little fuzzier than it should have been, but the details are written out in the paper. Okay, and this mapping is invertible, which is to say, given a clock auction, you can do this and create the corresponding deferred acceptance auction too. Okay, so a cutoff strategy is bidder J plans to exit at any price below BJ using only its own current price information. And the theorem is that every deferred acceptance threshold auction then is strategically equivalent to some descending clock auction with cutoff strategies. Let me remind you what strategically equivalent means. Strategically equivalence means there's a one-to-one mapping between the strategy spaces that's outcome preserving. It's the same algorithm, so of course. And conversely, every descending clock auction with cutoff strategies is strategically equivalent to some deferred acceptance threshold auction. So these are the same classes of auctions. They're just implemented differently. But we like clock auctions better, strictly better. Okay? Why is that? First of all, strategy proofness is obvious. All right? It's not that somebody tells you, tell me your value truthfully and I will do a complicated calculation and I will tell you what your price is, and believe me, it's in your interest to report truthfully. You don't even have to believe that I know how to do the calculation correctly. Ken, Eric, I've just offered you $50 million for your station. And you're saying, darn it, Paul, you were supposed to offer me $60 million for my station. You did the calculation wrong. Still strategy proof. Because when I've offered you $50 million, you still want to say yes if $50 million is above your value and no if it's not. It's just obviously strategy proof, and it doesn't even matter whether I'm computing the results correctly or not. Okay, so it's obviously strategy proof. Okay, so that's the second. There's experimental evidence from second price auctions and ascending auctions that bidders make fewer mistakes in the dynamic auctions. I guess this is really the same thing. It's just obvious what to do. In a second price auction, if you tell bidders it's in their interest to bid truthfully, they don't always believe you, and they make mistakes sometimes. They don't make the mistakes in the corresponding ascending auctions experiments.
There's also evidence suggesting they may not know their value themselves at the outset.
In real auctions, yeah.
In real auctions. Yeah.
So let me come to that. This is about the experimental evidence. In real auctions, that's exactly what you're talking about now. My third point is that we have the bidders out there, and there's the schmuck factor. And you're there, and you're worried that you're going to sell your station for $20 million when it was worth $50 million. That's what you're afraid of. And I can run this clock auction revealing a lot of information to bidders. I can tell you, there's 10 other bidders in your area who are the clock's at $30 million and they're offering, and that makes you a lot more comfortable about letting your station price fall to $20 million than if I keep you completely in the dark. So this is. I don't know what you want to make of this, but we think that in fact bidders don't know their values, and that the clock auction, again, this isn't a theorem, but we think the clock auction will make them more comfortable, particularly if we reveal a lot of information during the auction about what prices are being accepted. Improves bidder confidence. Oops, and these are out of order. Bidders with low profits may not need to compute their values exactly to bid optimally. If your station is worth $1 million, the hedge funds are going around buying up bankrupt television stations that have no business left because they have a license that they're going to be able to sell in the auction. You don't have to know always what your value is in order to be able to bid optimally. And there have been second price auctions. There's a famous example in Australia, in New Zealand, from 20 years ago, where there was a second price auction where the highest bid was $1 million and the second highest bid was $6. And it made headlines. Right? We don't want headlines like that, right? One of the things about a threshold auction is nobody knows that when Eric is being paid $50 million, when he would have sold for $20 million, nobody knows that he would have been willing to sell for $20 million. So one of the good things is that this can be done based on the economics rather than based on the optics. We can build an auction that's economically smart and not worry about political criticism in the press that's misinformed. Okay. Okay, now I put this here because I was afraid I wouldn't get to it if I put it later. I'm going to do more theorems if I have time. But I do want to show you how it all goes together and how Marshallian dynamics ends up being helpful to us in the auction design. So how are we going to, how is the FCC going to determine how many licenses to clear? So here in some detail is the process. We expect before the auction, before any auction begins, we are going to ask stations to register for the auction. We're going to determine opening prices, and we're going to say, here's the opening prices. Eric, the opening price for your station is $100 million. Do you want to register for the auction or not? And then I'm going to get a set of people who are registered, and I'm going to run an optimization. I have plenty of time before the auction. Figure out what's the best I can do with this set of stations in terms of clearing a lot of spectrum. And I determine, you know, I can clear all the channels from 31 to 51 if I do this well. And I can pack if I bought all of these guys, I could pack the remaining stations into the channels 30 and below. And I could clear all the spectrum from channels 31 and above. And so that's an optimistic number, but that's the most I could possibly do. And so that's my initial quantity. Okay? Now, I'm going to start there with that initial quantity. And somewhere in the background, there's, and this is, I'm pretending that the products are homogeneous, which they're not. But somewhere in the background, there is a supply curve and a demand curve that at this quantity, the reason I'm getting this quantity is I'm offering really high prices to the television stations, but the mobile broadband companies would never be willing to pay that much. Okay, in this picture. Who knows what the real picture is, but in this picture, they wouldn't be willing to pay that much. If they would be willing to pay that much, I'm done almost. We'll start it. But what's going to happen is the price falls in my reverse clock auction, and I got a forward clock auction for the mobile broadband providers, and the price rises. And oops, if I'm the government, the price that I'm paying for TV stations is more than the price that I'm getting from the mobile broadband guys. That doesn't work. So I reduce my quantity target and say I can't clear that many channels. And I let the price continue to fall in the reverse auction. And I let the price continue to rise in the forward auction. So the scoring, if you will, now makes a smaller set of channels available. Okay? But unfortunately, that still doesn't work. So I let the quantity traded continue to fall. And the price continues to fall in the reverse auction and continues to rise in the forward auction. And I have met my net revenue target. Now, by the way, there is a net revenue target. It will be determined by the politicians. It's above my pay grade. But among the things that that go into that is we have to raise $1.75 billion to pay the retuning costs of the stations that are forced to move during the retuning. We have to raise $10 billion approximately to pay the cost of the FirstNet public safety system. And the Democrats and Republicans differ about what the remaining objective is. That is, how much more money the auction should try to raise for deficit reduction or other purposes. Okay, so there will be some net revenue target, and there'll be a gross revenue target too. There'll be a closing condition that depends on comparing all of that.
And if the target's not met, then the auction's off.
If the target's not met, the auction's off. So we have the whole hypothesis of this repacking is that the low-value stations, the values are much lower than they used to be, and that there's a drastic need for spectrum in mobile broadband. And in fact, we have transactions prices for mobile broadband, and they're way higher than any transactions prices in broadcast television on a per megahertz pop basis. So if you take the prices, and you know what, I'm not going to say anything about the actual numbers here, but if you take the prices at which television station transactions take place and convert those into prices per covered household and convert those into the mobile broadband price per pop in the coverage area, you get numbers that are mostly lower and often much lower than the prices that are being paid, let's say, in radio spectrum auctions and also in transactions. T-Mobile brought some spectrum from Verizon recently for $1.85 a megahertz pop. AT&T has promised in a public filing that they would probably buy 20 megahertz of spectrum at a price of $1.50 a megahertz pop, which is a high price relative to what most TV broadcast things. So we have an expectation that this will happen. But of course, the auction will tell us. Okay? Yeah. Yes, right. It's not Germany. Yes, you may have heard. I mean, in Italy, right? It's really amazing how bad some of the spectrum auctions have run around. In Italy, they actually had to go to the study, and they weren't allowed to have internet communication to the outside to bid. The Germans had this really old technology too, where they communicated the bids into a center where they had to be individually submitted. I mean, the internet exists today. It is possible to do remote bidding securely, and so this will be done remotely, I assume. The government will decide, but we've designed this so that it can be done remotely. Or we've proposed the design. I'm not supposed to say. We've proposed the design so that this can be done remotely. Okay, group strategy proof. Every clock auction is group strategy proof. How much time do I have? Not much. So why is it group strategy proof? It's actually very easy to see. If you have a clock auction going on, suppose these 4 people in the front row are all participating in some coalition, and they say, gee, we can change our bids in a way that makes us all better off. So suppose that Ken is the first one to, during the auction, who has to change his bid. His clock is coming down. There's only 2 ways he could be changing his bids. He's either staying out when he should stay in, or he's staying in when he should be exiting, right? Well, if he is staying out when he should stay in, then he's losing, and he's getting a value of 0, so he can't be strictly better off. And if he's staying in when he should be going out, that means his clock price has now fallen below his value, so at the end of the auction, he's going to lose money. He's either going to not win, or if he wins, he's going to lose money, so he can't be strictly better off. So the first guy to deviate is going to be worse off. So there isn't any coalition that can deviate, right? So that's how you prove that the auction is group strategy proof. Okay, paid as bid comparisons. So this was in many ways the most surprising result in our analysis. We know from Bernheim-Winston, the menu auction, that when you run a package auction, a combinatorial auction where people bid for packages of goods, the equilibrium outcomes are in the core. And we know from an analysis that Larry Isabel and I have done that the Vickrey payoffs are always weakly higher, and the seller's payoff is always weakly lower than in any core payoff. So that means that the Vickrey auction never does better and sometimes does worse than a paid as bid auction. It's costly to provide the incentives. So it's rather surprising that that's not what happens here. So let me say in what senses it's not what's happened here. An auction is full information dominant solvable if iterated deletion of weakly dominated strategies in any order leads to a unique allocation and unique prices. And for non-bossy auctions, the order of deletion never matters. That's a theorem of Leslie Marks and Jeroen Swinkels. So that's where non-bossiness comes into our analysis. So assume discrete bids and finite reserve prices. One profile that's consistent with both iterated elimination and undominated Nash equilibrium has each station bid the greater of its rounded up value or its threshold price. And so that's this theorem, and that means that the winning bids, the winning bidders are paying their threshold prices because they're bidding their threshold prices. So we're getting the same allocation and the same prices. A paid as bid, non-bossy monotonic auction is dominant solvable if and only if it's a deferred acceptance auction, and it has a unique undominated Nash equilibrium outcome. So this is, I realize I said that quickly, but the point is that if you have an auction that's dominant solvable, you can figure out, okay, what are the prices that I would eliminate at the first round and make those the clock prices at the first round. And then you can figure out, okay, what are the prices that I would eliminate at the second round and make those the clock prices at the second round. You can construct the rule for different values by which you would decide what bids are eliminated. And so you can use the dominant solvability algorithm to construct a clock auction. And so you can show that if the auction is dominant solvable in the paid as bid setting, then there's a clock algorithm that reproduces exactly the same outcome. And so the winner selection rule is a deferred acceptance rule. Okay? So the only dominant solvable auctions are paid as bid auctions are deferred acceptance auctions. Okay? Proof is if, proof is only if. Oh boy, I actually have a minute to talk about Meyerson-like stuff. Okay, I didn't expect I was going to get to here. What if you actually wanted to optimize, that is to minimize the cost to the government? Okay? Suppose, right? This is a theoretical exercise. The government doesn't want to actually minimize the cost. But as a theoretical exercise, suppose that you had an auctioneer that did. So the problem is to minimize the total expected payment. Where you think of X, basically T's are the transfers, X is the assignment, so this is how much somebody pays as a function of the vector of cost C. When they're assigned with this probability. It's the usual optimal auction formulation. Subject to the incentive constraints, which are the usual incentive constraints, and subject to the participation constraints, which are the usual participation constraints, and subject to the feasibility constraints, which is the only thing that's different. So when you write this auction down, the only way this looks different from Meyerson is that the set of bids that you're allowed to accept is different. Okay? So incentive constraints identical. The participation constraint actually is reversed because it's a procurement auction rather than a sale, but it's the same constraint. The analysis begins identically to the Meyerson analysis. What do? You replace the incentive constraints with monotonicity in the envelope formula, just like you do in Meyerson. You substitute the payment. You use that gives you how the price depends on the allocation. You substitute that into the objective function. You reverse the order of integration. All that beautiful stuff that Meyerson does for those of you who have studied optimal auctions. And what do you get? So what you get is you get that you get the problem of minimizing the expected value of what Meyerson calls the virtual values subject to the feasibility constraints. And in the regular case, that is solved by minimizing for every realization the sum of the virtual values subject to the feasibility constraints. So you get a beautiful, clean theory that tells you exactly what the optimal auction is in this hugely complex setting. You minimize the sum of the virtual values just like you do in Meyerson. You just apply a different set of constraints. Okay? So what would you do? So if you're trying to do an optimal auction, what you would want to put in is you'd want your scoring rule to map the values into the virtual values, okay, into the Meyerson virtual values. And if we wanted to do that, I could tell you some ideas about how to do it, but it's not what we're trying to do, and the government doesn't want me to talk about how we would do it. So I won't tell you, but that's the idea. You can use this to formulate the optimal auction problem. Then you can use a heuristic, a greedy heuristic that does a good job of optimizing, pretty good job of optimizing to come close to the revenue maximizing auction or cost minimizing auction instead of coming close to the one that is most efficient. Okay, so you could do that. And so I got through it. How about that? Thank you. All right, it's 11 o'clock. I'll see you guys in half an hour.